my son. Good evening, everybody. It gives me great pleasure to bring on behalf of the Quantum Center for Diamond and Emergent Materials, QuCenDiEM, the 9th talk of our Quantalks series. This colloquium by Professor Arie today brings the best of two worlds to us, the world of quantum science and technologies, as well as the colorful world of photonics. Indeed, today is a very special day to bring to you a talk on photonics, because today we celebrate the festival of colors, that is Holi, here in India. Indeed, I wish Professor Arie and other colleagues were to be in person today. You would have really seen the vivacious and delightful spirit in this country. Nonetheless, keeping all that in spirit, we can have a lot of insights into photonics and quantum science today through this colloquium. To introduce Professor Arie, Professor Arie received his bachelor's degree in mathematics and physics from the Hebrew University of Jerusalem in '83. In '86 and '92, he received his MSc degree and PhD degrees respectively in engineering from Tel Aviv University. Between '91 and '93, he was a Wolfson and Fulbright postdoctoral scholar in the group of Professor Robert Bayer in Ginston Laboratory, Stanford University. Professor Arie is a recipient of numerous fellowships, awards, and recognitions of his scholastic achievements. In '93, he received the Allen Fellowship for new faculty members from the Israeli Council of Higher Education and joined the Department of Physical Electronics School of Electrical Engineering in the Fleischmann Faculty of Engineering, Tel Aviv University. In 2006, he became a professor of electrical engineering. However, before that, between 2001 and 2005, he also served as a co-founder and chief technology officer of a startup he co-founded, Zeta Light Incorporated, in the field of optical wavelength management. Professor Arie served as the Vice Dean of Research for the Faculty of Engineering in between 2011 and 13, and headed the School of Electrical Engineering between 2013 and 17 at Tel Aviv University. He is currently the head of the Tel Aviv University Center for Light Matter Interaction and the incumbent of the Marco and Lucy Shaul Chair in Nanophotonics. In 2016, he won the prestigious Kader Foundation Award for Excellence in Research. Professor Arie is a fellow of the Optical Society of America, the preeminent institution for physicists, engineers, and scientists in the field of optics and photonics, which has a long tradition and history. In the years 2008 to 14, he served as the topical editor of the very prominent and historic journal Optics Letters, and since 2018, he is an associate editor of the new top-ranked journal Optica. He is also the chair of the National Steering Committee of the Israeli Planning and Budgeting Committee on Quantum Science and Technology. In his recent years, his interests have been quite varied in the areas of classical and quantum nonlinear optics, hydrodynamics, electron microscopy, and plasmonics. Professor Arie is a mentor to over 39 PhD students. He has over 35 competitive research grants, and he has mentored several postdoctoral fellows, some of whom actually hold positions now in India and overseas. With this brief and definitely not exhaustive CV of Professor Arie, I'm indeed delighted to welcome you, Arie, to present your colloquium today on the generation and control of spatial qubits.
Okay, thank you, Siva, both for the introduction and for the invitation. It's really a great pleasure and honor for me to be here. Let me share the screen. So I'm really, I hope that next time I can do it. I can come to India and meet all of you in live. But now that I guess this is as best as it can get. So I'm really delighted to be here and to see good friends that I have that are joining. I'm going to talk about some activity we are doing in the recent years in quantum optics. So we know that we are now in what is called the second quantum revolution, and quantum optics is playing an important part of it. And I will talk about some specific aspect of it, which relates to generation of quantum light. Specifically, this is generated by a process of spontaneous parametric down conversion. I will explain a bit about it. And also the emphasis is on using a specific degree of freedom, which is the spatial degree of freedom. So this is the outline of the talk. First, I want to talk about some the spatial degree of freedom of light, mainly of quantum light, and how it can be used for quantum key distribution, for sensing, and for quantum simulation. I will talk about the process that we are using in order to generate it. This is a spontaneous parametric down conversion. So we spend a lot of work, and I will describe some of it, on developing tools to simulate these processes, also to use it using an inverse solver in order to generate a desired state. I will show some examples of this for generation of spatial qubits, qubits, and qquarks. I will show very recent experimental results. Actually, they are not published yet. This is the first time I show some very recent results on direct generation of Bell states in the Hermite-Gauss basis using structured crystals. And also some recent work that we are doing together with a company, with Recall crystals, on manipulating the spectral and temporal domain. And the last part of the talk will be on a special class of states, which are called Nun states. And I will show a new method to generate them using structured crystals or using shaped pumps. And I will show how this can be used for sensing, specifically for super resolution in phase measurements. So first, let's talk about how to encode information on photons, on single photons. So a lot of work was done, still is being done to use polarization, the polarization of light, in order to encode the information. So, for example, we can use linear, horizontal, and vertical polarizations. These are this is two orthogonal base vectors, or we can use diagonal and anti-diagonal. These are also two orthogonal base vectors, which are mutually unbiased with the HV base. This is widely used in many applications in quantum optics, but the main issue with this is limited. The polarization is essentially a two-dimensional, spans only a two-dimensional Hilbert space. So maybe we can use some other degrees of freedom. So I didn't know that today is the Festival of Light in India, but one of the things we can do is we can use the wavelength as a multi-dimensional basis. I will talk a little bit about it. And the other option is to use the shape. So this is an example of different modes that we can use. This is the Hermite-Gauss family of modes. And this is, again, a multi-dimensional basis. More specifically, there are different families of bases that we can use in the spatial world. I will mainly emphasize Hermite-Gauss modes, which are shown here and are described by this. And the other family of modes is Laguerre-Gaussian modes, which are shown here. So these two modes, each one of them is an orthonormal family of modes. So they can be very useful. The Hermite-Gauss modes are solutions of the Paraxel-Helmholtz equation in Cartesian coordinates. So it means that these modes, they preserve their shape when they propagate in free space. They only change the size owing to diffraction. And like similarly, Laguerre-Gauss modes are solutions of the paraxial Helmholtz equations in cylindrical coordinates. Another interesting property of Laguerre-Gauss modes is that they carry orbital angular momentum. If you look the phase of these modes, there is this component IL-phi. L is an integer. So it was shown that these modes carry orbital angular momentum, which is h bar L. And also, like we discussed before for polarization modes, HV or diagonal anti-diagonal, that are mutually unbiased. Also, the Hermite-Gauss and Laguerre-Gauss family are mutually unbiased. But this is a d-dimensional modes. I mean, if I use here even just this is just a subset of the modes. There are already 12 modes that I can use here. So the spatial degree of freedom is very useful to encode information. By the way, not only for quantum light, also for classical light, it is used in spatial division multiplex, optical communication, both in free space and now also in fibers, in order to increase the capacity of optical links. But in quantum optics, these modes, they serve as an alphabet, a d-dimensional basis, and we can use them to form qubits. So usually we talk in quantum optics or in quantum mechanics about qubits. So qubits is a d-dimensional quantum digit. Okay, just to illustrate it, let's consider, for example, the Laguerre-Gauss family. So here I'm showing only 7 modes out of the infinite number of modes. By the way, this is the intensity pattern and the phase pattern. So this is the 0-order mode, this is the +1, this is the -1. They have the same intensity, the +1 and -1, for example, look the same in terms of the intensity distribution, but the phase pattern is different. If you look, this is the phase, this is the helical phase for the +1 and the -1. You can see that here it rotates clockwise, and here it rotates counterclockwise. And I can even just take 2 of them, this +1 and -1 mode, and I can use it as a basis. And with this, I can form a qubit in the LG basis, and I can even show it on this Bloch sphere. So these are the +1 and -1 mode. On the Bloch sphere, on the equator, I have this would be superpositions of these 2 modes. So this would be Hermite-Gauss. And here I used only 2 of them. There are only in this figure there are 7, but in principle there are infinite number of modes. So this is very flexible. Now, next thing I want to discuss is how to generate quantum light. And the main process that it is used, not only by us, but by most people in this field, is based on spontaneous parametric time conversion. So this is a nonlinear process. It can be second order or third order nonlinear process. We focus on second order nonlinearity. So we have a nonlinear crystal. We send the PAM beam, and then we have spontaneous breaking of this PAM photon into 2 photons, which we call signal photon and idler photon. And this process has to maintain energy and momentum conservation. Why is it so much used? Because it's a relatively efficient process. It can work at room temperature, and it's fairly flexible, as I will show you. I can do many things. I can modulate the PAM. I can modulate the nonlinear crystal. So I have many ways to control this process. Now, just to show that actually the spatial degree of freedom is already used for many years, I want to show this is a very famous experiment done by Meyer and Zeilinger more than 20 years ago. You can see this is a very famous paper because it has more than 3,000 citations. So what they did is they did this process that I described, the spontaneous parametric time conversion. There is a nonlinear crystal here, they send a pump, and then this pump breaks into a signal in idler. And what they do is they analyze the shape of the signal in idler. And for this, they use masks. They use these fork-shaped masks. So these masks convert Laguerre-Gauss modes back into a Gaussian modes, but only for a specific mode it works. So once this happens, this mode will be coupled into a fiber and reach the detector. And if we have coupling for the two detectors, we'll get a coincidence. So what they've seen, what they've shown is that the coincidence are always on these diagonal lines, where, for example, if we concentrate on this one, there is a coincidence when the signal OEM is +2 and the idler is -2, or +1, -1, or 0, 0. So always the OEM of the signal and the OEM of the idler equals the OEM of the pump. If the pump is a simple Gaussian, then this is what is shown here. If the pump itself is a Laguerre-Gauss mode, then we take this diagonal line, then we can shift it. So then the sum will be, let's say, -1 in this case, or +1. So what I wanted to show is that actually, even without doing any structuring, not of the pump nor of the crystal, you already get structure the signal and idler photons. Now, why spatial degree of freedom is interesting? So I will discuss some applications. So one very important application for quantum light is quantum key distribution. This is a way to transmit the keys between two parties in a secure manner. And again, our reference or benchmark is QKD with a two-dimensional basis, for example, using polarization. So using QDITs, for example, spatial QDITs, give us several advantages. One is that we can transmit more information per photon. If we use D-dimensional QDITs, then we can have log 2D bits instead of 1 bit per photon. Also, or maybe even more important, is that when we go to higher dimensions, we have improved security. So we can look at this table. This is the dimension that we use. This is the two-dimensional case. This is what is the error threshold that is guaranteed. So we can see that as we go to a higher dimension, we can have higher threshold, higher error threshold. This means that, in fact, when we use higher dimensions, we can consider that the transmission to be more safe against attacks. And finally, we can use spatial degree of freedom together with other degrees of freedom like polarization or wavelength and get even higher dimensional communication. And this is already used by different groups, both in free space and in fibers. So this is an example that was done by the group of Anton Zeilinger in Vienna, where they used the Laguerre-Gauss beams. Here, this is Ibrahim Karimi and Robert Boyd use structured beams in Ottawa. Both these examples are in free space, but also in fibers. We have now vortex fibers. These are fibers that support different modes that carry OEM with minimal mode coupling. So it was also shown that we can use the spatial degree of freedom for QKD in these fibers. And then another application is in sensing. For example, here these are two works. One, this is by the group of Boyd, and this is a recent work by the group of Robert Fickler. But in both of them, what they show is that if you use vortex beams, for example, we can use this combination of vortex beams, then we have super resolution for angular measurements. We can measure, if we put a mask and we rotate it, we can have better sensitivity when we use these beams with respect to classical beams. And finally, also for, I mean, there's no quantum computing yet, but maybe for quantum simulation, this could be something interesting. So again, there are the advantages I described before for of higher dimensions. But then the question is, can we get gates that manipulate these processes? So this is something that was shown recently by the group of Fickler, where they realized different types of gates like Hadamard gates, X gates, and so on. And the way it's done is that we have a structured light, then we go through multiple passes to a spatial light modulator. In each region, we put a certain modulation, and this way we can realize these gates. So this is kind of a step toward the simulation or computing using the spatial degree of freedom. And question is how to generate the spatial degree of freedom. So I showed you what Zeilinger and Meyer did, but what's usually is done today is that we generate in SPDC, we generate beams which have Gaussian shape, and then we just use an external mask, use a spatial light modulator or sometimes a Q plate in order to generate the shape that we want. And what I want to show is that there is a different approach, which is by properly designing either the crystal and or the pump, we can actually shape directly the photons that are generated, and we can generate states with the desired spatial property. For this, we need to be able to modulate the nonlinear coefficient of the crystals. There are different ways to do it. One way, which is called electric field polling, this is done in ferroelectrics, is a fairly established process. It's now commercially available. It enables to modulate crystals in 2 dimensions with very good performance. And now also in the recent years, there was a kind of a breakthrough. There's a new method to modulate the nonlinear coefficient in 3 dimensions using laser writing. So both of these are now available. This one is available commercially. This is kind of available if you have good friends that can make it for you, but essentially it exists. So, and now I want to move on and talk more specifically about our works. So one thing that we thought is very important was to have a good tool to design the process, the spontaneous parametric down conversion process. And what we did is to develop a simulator that can handle structured pump beams and also structured crystals. And it can predict different parameters in the spontaneous parametric down conversion process. Specifically, we can predict the first order correlation, G1 correlation, which is essentially the detection probability. It means that if we put a camera, what we will see in different pixels. This is the G1. And the other process, the other parameter that we want is to learn what is the second order correlation, G2. So G2 is essentially what happens when we do some correlation between 2 detectors. Each detector will measure a different mode. So the goal of this simulator was to be able to calculate this for different shapes of pumps and for different shapes of crystals. And this, the key people here are Sivan Trachtenberg-Mills. She's a former student. She already graduated. She's now doing postdoc in MIT. And Aviv Karnieli was a very brilliant PhD student in my group. Before I do it, people may ask, is it possible to do it at all? Can we simulate quantum systems using classical computer. So in fact, Richard Feynman, who was a key person also in the proposal to make quantum simulators and quantum computers, he looked at this case, and there is actually a talk that in which he discussed it. And the main conclusion is that it's not possible. So of course, it's not a good idea for me not to be in agreement with Richard Feynman, but let me first explain why he says it's no, and then I will say why actually we can still do something with a classical computer. So first I will explain why Feynman thought the answer is no. So it's not that it's not possible, it's only that it's very complicated. So the case he considered is the following. We have, again, this spontaneous parametric time conversion, and we have an idler, and we have a signal. And then the idler is detected, or the signal is detected in one camera, and the idler is detected in the other one. And so let's assume that we have like 512 pixels by 512, each one that represents a different k vector. And let's even simplify it, and we say, okay, in each what we can have in each pixel is either 0 photons or 1 photon. Okay. Of course, it can be more than 1 photon. It can be more complicated, but let's even limit to only to this case. So there is a huge number of possibilities for this problem. So obviously, if I have to go and calculate all these possibilities, this would be something which is, I mean, maybe I can do it with a very, very large computer, but it's not very practical. So why still we can do it? Why still we can use the classical computer and do something useful? Because in practice, we don't actually need to go over all these 512 by 512 points. The cases that are usually generated are spanned by a much larger, by a much smaller subspace, and moreover, averages, which are mean, variance, and correlations, can be computed by a classical computer. So, as I said, it's not a good idea not to agree with Feynman, but I think there is for SPDC, and in most cases, the problem is simple enough that it can be done with the classical computer. And I will show you that what we are getting is in very good agreement with what people have measured in experiments. So I'll briefly explain the method we use. So one thing I want to say that the calculation is not a semi-classical calculation. We actually do a quantum calculation. There are some approximations. I'll just explain one of them. So what we assume is we have this nonlinear crystal, and we have a signal wave and idler wave that are generated. And we limit ourselves to the paraxial approximation. This means that all the k vectors that we look at are centered around some central k vector. For example, for the signal is this ks0, let's say, and then the addition is small with respect to that. And same for the idler. So when we do it, what we can do is we can use what is called the paraxial envelope operator, which is essentially spanned only using these q vectors. And now what we want to do is we want to calculate first the first order correlation. So this is the first order correlation. But for SPDC, the state that we look is the vacuum state. So in fact, this is the first order correlation, and in order to calculate it, what we do is we have to go over all the possible modes. So in this example that I showed before, it would be going over all these 512 by 512 modes. So this could be indeed a very tedious calculation, but what we can do instead is we can use, instead of using these k vector modes, we can use what we call white noise modes. So this is kind of a superposition of modes, each one with some random phase. So let's say if I look at some plane, it will look like this. It's not like a dot in the fast field. Before I have one dot, here I will get something like this. I need many realizations of this. These are our white noise modes. And once I use them, I can relatively quickly converge to and get the first order correlation. So this is the first order correlation spanned using these white noise modes. Now, what I want to emphasize, this is now a number and this is a number. So I just need to average over them. And in fact, I can define 4 different parameters, which are shown here. So it is the operators sandwiched between the vacuum mode and the white noise mode. And I can, in order to see the dynamics, I need to go to the Heisenberg equation, which under the assumptions of small walk-off is just this. I'm just getting this equation, which is essentially an equation that we are very familiar with in nonlinear optics. So what we have here, this is diffraction, and this is nonlinear coupling. So we have it both for the idler and for the signal. And we have to do it for these 4 different parameters that I wrote here. So in fact, we have 4 equations, 4 coupled equations that we have to solve. We can do it numerically. 2 of them are for these vacuum noise modes, and 2 of them are for the output modes. And these equations are the same. We can solve in the same way we used in classical nonlinear optics. So in fact, what we got in the end is we have now a numerical tool to calculate the first order correlation. I mean, I outlined all the assumptions, like it's paraxial, and I assume that I can neglect group velocity dispersion, but essentially that's it. So just to show you that it works, let's look at a few simple cases. This is the case where we send light to a regular crystal. So the far field pattern should be a ring. Why is it's a ring? Because you can see that there is kind of a symmetry around this axis. So every pair of signal and idler would satisfy phase matching and energy conservation. And indeed, for this simple case, we see that indeed we get the ring. This is now a result from this simulation. Okay, so this was a simple case. Let's show a more difficult case. So what we have here is a 2-dimensional crystal, and moreover, we can tilt the beam. So in fact, this is more difficult to calculate because there are many K vectors. Each one can contribute. And when we tilt, it's even becoming more complicated. So this is a measurement. This is what we see when the crystal is straight. This is what we simulate. And now we can start rotating this crystal at different angles. This is what we measure. This is what we calculate. So you can see that this tool works very nicely. You can calculate very accurately the first order correlation. Next, we want to measure the second order correlation. So the key idea here is that, in fact, we can use the fact that the SPDC is a Gaussian state. And if it's a Gaussian state, then we can have higher order, we can calculate higher order moments. In this case, it's a second order correlation from the lower order moments, which are the first order correlations. So first order correlations, we know how to calculate. So it means that using this, we can also calculate the second order correlation. And again, I'll show you simple cases first a simple case and then more complicated case. The second order correlation, again, for this simple case of pump and a crystal, we showed before that we get the SPDC on a ring, but the correlation is only from adjacent points. If we measure a click here, we should measure a click here only, because only this pair satisfy the simultaneously the phase matching condition. So this is shown here by calculating the second order correlation as a function of θ1 and θ2. So we can see that there's always 180 degrees difference between θ1 and θ2. And another nice thing about this simulation tool is that it can also predict higher order correlations. In this case, it's a 4-photon correlation. Now, this was a simple case. Let me show you a more difficult case where we pump with Hermite-Gauss. This, in fact, was an experiment. It was done by Quantalks co-workers. So they use a Hermite-Gauss pump. And in that case, this is the correlation matrix. So they had high correlations only for 2 cases. And this is why it's kind of a bell state for Hermite-Gauss modes, which is written here. So either the signal is Hermite-Gauss 0, 1 and the idler one is Hermite-Gauss 0, or vice versa. This is why it's a kind of a bell state. All the other modes have very low probability. And what we see is that the simulation actually reproduces these experimental results. And also the experiment of Meyer and Zeilinger that I showed you before, that we get when we send light to a regular crystal, then if these are 2 OEM modes, if this is +1, this is -1, if this is +2, this is -2, and so on. And in any case, they just sum up to the OEM of the pump. We can also see this. So we checked here different cases with different pump OEM, and as in the case of Meyer and Zeilinger, they always lie on these diagonal lines. And these diagonal lines move because we changed the pump OEM. Okay, so far I showed you how to calculate first order and second order correlations. But now what we want to do is we want to invert the problem. So what we want to do is the following. We want to get at the output a certain state. This state should either have a desired second order correlation matrix or a desired density matrix. And the question is, what should be the shape of the crystal and what should be the shape of the pump in order to get it? So this is an inverse problem of what I discussed before. And we worked on this. The key person here was Eyal Rosenberg, but also other students from the group, Aviv Karnieli, Ophir Esharim, Josh Foley-Comer, and Sivan Tachtaner-Mills. And we also collaborated with Daniel Friedman from Google and Alex Bronstein from the Technion. So in fact, we used a machine learning tools in order to find this problem. And this can be shown schematically here. So we want a certain output. The output can be defined, as I said, either using the second order correlation or using the density matrix. And for this, we parameterize the pump and or the crystal. And what we do is we train the system in order to minimize some discrepancy between what we get when we run this in the forward model and what we desire. And the discrepancy measures are for G2 could be L1 or Kullberg-Libler divergence. And for the density matrix, it's just the trace distance. So this works very nicely. I'll show maybe just a few examples. For example, coming back to the experiment I showed you before of Kovlakov, where he showed that he can get a Bell state when he pumps a regular crystal with Hermite-Gauss 0 and 1 mode. This happens only for a certain value of the pump waste. And what we did in this test is we said, okay, we want to learn what is the size of the pump waste that will give us this desired state. And here you can see different iterations, and eventually we get to the value that is used in the experiment. Then once it works, we can do some more sophisticated cases. For example, we can now, let's say we want to generate a qubit in the Laguerre-Gauss basis. So we want to have only 2 modes. So this is our target in the G2 matrix, in the coincidence matrix. And in this case, we learn only the crystal. The pump is a simple pump. It's just a Gaussian pump. This is the shape of the crystal that we get. Okay, it's kind of a sophisticated shape. We need 3D polling capability. But once we do it, once we run this simulator, you can see that we can get something which is very close to our target. And moreover, once it works, we can now change the pump from a Gaussian pump to Laguerre-Gauss 0 and 1 pump. And same as what Meyer and Zellinger showed, we can have this qubit to this biphoton qubit, we can just move it to a different position. So we'll get different correlations of signal and Euler. And this can go on. I don't want to show all the cases, but for example, maybe this a bit more sophisticated case which utilizes the higher dimensionality of spatial modes. So in this case, what we want to do is we want to generate a QQuart. So in fact, we have in this correlation matrix, we want to have four options that are written here. And you can see that we can learn it. We can design a crystal. This is the shape of the crystal. It's quite sophisticated. It requires 3D modulation, but essentially is doing what we want. We will have only correlations for these 4 options. And also here we can do coherent control. We can take these 4 coincidences and we can move them to the left or to the right by changing the pump shape. Okay, maybe I'll skip this. I just want to say, so we can either change the pump, or we can change the crystal, or we can change both. So this is just to show the options that we have. Here we have again we want to generate a QQuart. If we generate, we can use either the nonlinear crystal, but you see it's not perfect. They are not the same, and there is some unwanted correlations here. We can use only the pump. Again, it's not perfect, but if we use both of them, still not perfect, but much better than each one of them separately. So it shows that in some cases we need both the pump and the crystal. Okay, so now I want to discuss briefly a recent experiment. Actually, it's the first time I'm showing it, I think, in public, where we use these tools of designing crystals in order to generate or to control the shape of SPDC. And the target here is to generate a Bell state in the Hermite-Gauss basis, but this time using the crystal. Before I showed you the experiment of Kovlakov where we use the pump. Here I'm going to use a regular pump, it's just a Hermite-Gauss pump, but the crystal will be shaped so that it will generate, for example, the signal will be Hermite-Gauss 0, the Euler will be Hermite-Gauss 0, 1, or vice versa. And there are also limitations in the fabrication of the crystal. Not every shape that we want can be fabricated. In the crystals that we work, which are KTP crystals, maybe we would like something which is more round and smooth, but it's not possible. So still we had some limitations. But nevertheless, we said, okay, let's use our tools and design the best crystal that they can manufacture. And this is the shape. This is now a crystal that was fabricated. We look at the top surface after etching, so it reveals the modulation of the nonlinear coefficient. We tested by second harmonic generation, so we saw that we can generate a mid-Gauss 0-1 mode. And also we did now a SPDC and measure the correlations. So this is the pump, this is the crystal that I discussed before. It's a type 2 process, so we can split the signal in idler, and we can use this SLM in order to encode different masks, so we can test different shapes of the signal in idler. And what we see is this correlation. So we can see that there is very high correlation for these two cases. In one of them, the signal is mid-Gauss 0-1 and the idler is mid-Gauss 0-0, or vice versa. In this one, the signal is mid-Gauss 0-0 and the idler is mid-Gauss 0-1. So it's very close to what to this Bell state. It's not perfect because you can see that there is some coincidence in others, but the coincidence for these two modes is much higher than all the others. And just as a reference, if we use here a regular crystal, then we are left essentially only with the mid-Gauss 0-0, both for the signal and to the idler. So this shows the power of the modulation of the crystal, that it can affect the shape of the generated photons. This is the density matrix for this case. Again, it's quite close to the theoretical case for Bell state. So I talked a lot about the spatial degree of freedom. Let me say a few words about the spectral degree of freedom. This is also a very useful degree of freedom. It's again multidimensional. And recently we extended our simulation tools to design crystals where we utilize the spatial degree of freedom. So in general, the SPDC can be written like this. So it's kind of an integral of signal and idler frequencies. There is one signal photon, one idler photon. And in fact, the process is characterized by this function, which is called joint spectral amplitude. But this work is done by Imbar Horowitz and Aviv. There is some noise that I hear.
Sorry, Amit, could you please mute yourself?
Yes.
Thank you. Please go ahead, Arie.
Okay. So I'll show you two examples. This is an example. I mean, there are many details. I'll not go over them, but essentially the idea is the following. I want to have a special shape of this JSA, of joint spectral amplitude. So as I did in the spatial degree of freedom, I can use shaping of the pump. In this case, this is the shaping of the pump. This is idler wave and this is signal wave. This pump has two peaks. It's a kind of an mid-Gauss 0-1 in the spectral domain. And here, this is a kind of a sophisticated crystal that has many options for phase matching. So if the overall result is what is shown here, is something that has, in this case, like 8 peaks. So it means like 8 different combinations of signal and idler that are efficient. This is a kind of a high-dimensional entanglement. But I want also to show the other extreme, which is also very useful. So if you just take a regular crystal, just periodically poled crystal, and want to measure the joint spectral amplitude, what you get is what is shown here. Okay, what is shown here. Why you have all these stripes? Because the phase matching function of this crystal is a sinc function, so it has multiple lobes. Now, for a specific application of heralded single photons, heralded single photons means that I'm measuring one photon and it heralds the presence of the second photon. So this is not a good result for that. Why? Because essentially it reduces the purity of the mode. When I detect the idler, the signal can be in one of several different modes. And if I, for example, want to do some Hongo-Mandel experiment or other things, it will actually would be something that hurts my performance. So what we want to have is something that looks like this. There's only one mode, only signal mode, only one mode, which is I described. Instead of having it like a kind of a superposition of different combinations, there is only one option. And this is what and in fact, using the tools that I described, we recently designed such a crystal. This is in collaboration with a company, Miracle Crystals. It's an Israeli company that makes crystal. So this is something that we think can be useful for heralded single photon experiments. Now, just to say briefly, the same as the spatial degree of freedom, also the wavelength or frequency degree of freedom is also very interesting, both for applications in simulations. This is an experiment by the group of Roberto Morandotti, first author with QuEst, where they showed the coherent control in the spectral domain, and also for sensing. It's very interesting. This is a work done by the group of Alex Gaeta using the spectral degree of freedom. So we need tools to be able to manipulate or control the shape of single photons in the spectral domain, and I think now we can have them. Okay, so last part of my talk, I want to talk about a special class of entangled states, which are called noon states. So what are noon states? It's what's described here. Essentially, it's we have two modes, A and B. So either we have n photons in mode A and 0 in mode B, or vice versa. So first you can understand why it's called noon state. And noon states are very interesting because they provide some, especially for sensing, because we can get super resolution in phase measurements with noon states. They accumulate the phase n times faster with respect to coherent state that we have from a regular laser. And the error in phase measurements goes as 1 over n with respect to what is called the standard quantum limits, where the error is 1 over square root of n. And this work is led by two, actually former members now. Giuseppe Di Domenico is a postdoc from Italy, and Shauli Perl. So let me show now how to generate. The question is how to generate this noon state. So the standard method to generate noon state is the following. We start with a regular SPDC process. So you already know that all the options lie on a ring. And now what we do is we put here an aperture and here an aperture, and we beat them on a beam splitter. And then if the two photons arrive simultaneously, there will be a Hongo-Mandel interference. So either we'll have two photons going this way or two photons going this way. So then we'll get this null state for n equals 2. However, this is a very complicated process. We have a crystal, then we have to do all the optics. We have to exactly match the paths in order to get this interference. So the question is, maybe we can do something better. Maybe we can design some crystal or some shape of the palm so that the noon state will emerge directly from the crystal without needing this all this tedious process. And in fact, this was studied in the past, both by our group, together with Hagai Eisenberg, and also in the group of Xining Zhu in Nanjing University, using two-dimensional crystals. But recently we came back to this idea because we thought that there is some other interesting opportunities. So one opportunity is to use a shaped crystal which has this form. We call this a Citroen crystal because if you know the logo of Citroen, it looks like this, the Citroen car. So this when you have this crystal, when we pass exactly in the middle, either we have signal and idler that are phase match in one direction, or signal an idler that I phase match in the other direction. So we will get a null state directly from the crystal. We'll get either 2 photons here and 0 here, or vice versa. And then we can do interferometry. One of the paths we can put some rotating window that will generate a different phase, and we can measure with 2 single photon detectors the coincidence. So this will be an interferometer based on crystal shaping. The other option is to use pump shaping. In this case, we use a regular crystal, and what we do is we just use crossed beams for the pump. And so actually the scheme is very similar. Again, we'll have only we have 2 photons in this direction or 2 photons in this direction, and again we can do interferometry to measure to see whether we have super resolution phase measurements. So this is again using the simulation tools that I described. We can look at the first order correlation and second order correlation. But even more interesting is these coincidence measurements. So this is for the shaped pump case. And this is shown for different powers of the pump. The most important thing is the following. So the phase shift is what happens when we rotate the angle of this window. So we accumulate different phase in one arm with respect to the other. And what we can see is that actually this phase changes twice as fast with respect to coherent case. So in every wavelength, we'll have two cycles. And this is fairly efficient. We have about 200,000 coincidence per second. So this is what is shown here. We also showed it with the structured crystal. With the structured crystal, it also works, but it's a bit more noisy because this process depends on the quality of the crystal, which was not as good, I guess, as we would like. But still, it shows that the effect works, and we can get this super resolution. So let me summarize. So I hope I convince you that the spatial degree of freedom can be very useful in quantum optics, and can be used for different applications like QKD, quantum sensing. In order to control it, I showed you different methods, either by shaping the pump or by structuring the crystal. I discussed in some detail simulation tools and inverse design algorithms, which we believe are very critical for the ability to design experiments based on SPDC. And I showed you some preliminary experimental results using either generating a Bell state in the spatial degree of freedom, or also how to generate states for a halted single photon experiments. And finally, the last part was on generating biphoton null states, where we showed the super resolution and fairly high rate of about 200,000 coincidence per second. And some of these works appear in these papers. And maybe the last slide, I'll just show you, this is a relatively recent group photo. So we usually have one group to group 3 per year. And so maybe this is Aviv Karnieli that I mentioned before. And I guess and this is Ophir Esharim that did the Bell state in their mid-Gauss basis. And this is Shauli. And I don't know where is Giuseppe, he's also here. I don't see him now. Okay, I don't see him, but he's in the picture. Sorry, it's just in front of me. This is Giuseppe and Shauli that did the non-state experiment. Okay, so thank you very much.
Indeed, thank you so much, Arie, for walking us through at a pace that we possibly can assimilate this well. That really opened up many dimensions also in our minds, I guess. So we can now take questions from the audience following this fascinating talk, and also revelations of new opportunities in structured light and quantum applications. Any questions, please either unmute yourselves and ask, or please raise your hand in case you want to prioritize yourself when an answer or question is going on. The floor is open. Hi, RP.
Hi, so may I ask a question?
Please go ahead, yes.
So, Arie, you say that you can shape the pump as well as you can shape the crystal. So, being an experimentalist, I have a feeling that shaping a pump is easier, much more practical. So, what is your experience like? Would you prefer shaping the crystal or shaping the pump, or both are required? Can you comment on that?
Okay, so thank you, RP, for this question. So you are right that it's more difficult to shape the crystal. So the question is why to bother? So I want to show something that maybe will explain it. So for example, let's take this experiment. Okay, so here we want to measure. Here we want to generate this. By the way, this state is already useful. For example, in Bell states are useful for let's say protocols like Eckert 91. So in order to generate it, okay, we had to invest before. We had to design the crystal and we had to fabricate it. But once we had it, you know, the generation is just, that's it. It's just the laser and the crystal. We don't need any SLMs. We don't need any beam splitters. We just go single pass through the crystal, and that's it. Mm-hmm. So the other part, I mean, for the detection, we need maybe SLMs and so on. But you know, now there are some experiments where they put sources on satellite or so on. So many times the source, you have limited resources. So you don't want to put some sophisticated optics or sophisticated instruments. And I think this is what this is offering, like the ability to have the generation state to be very simple. By the way, the same also holds for this case. I mean, also here, this is used. I mean, people are using standard crystals, and then they put filters in order to have only this part. But again, as I said, if you, let's say you invest, you have to do some investment in the beginning, in the design and fabrication. But once you have it, you just plug it and that's it. You don't need anything else. You don't need filters. You already get directly the state that you want. So we think this is the advantage.
Certainly, that is advantage, but technology for shaping the crystal is still not that popular. While SLM are available commercially, like quite popular. Most of the labs are having, which are working in structured beams and all. But shaping the crystal, hardly few groups maybe are doing. So it has to, like, we have to wait till it becomes a popular technology like SLM, so that you can get the shape crystal.
Yeah, I agree. I mean,
it's a robust, more compact and robust technique.
I agree, but we want to push the technology forward. So, by the way, like this, what I show here is from the website of Raycon Crystals. So now they offer this as a product. So I think this is I mean, okay, we need to do this investment in the design and fabrication, but after we did it, you know, if it's available and it already solves the problem, then for users it should be as easy as
for users it's quite easy. Thank you. Thank you, Arie.
Thank you for the question.
So it's a great startup opportunity perhaps for new generation entrepreneurs. Any questions? We could have the next question. Yeah, if people are thinking about it, I would probably Brajesh Kumar Singh, please go ahead.
Hello, Brajesh.
Hi. Yeah, hi, Arie. How are you?
Hi, very well. Hi, nice to see you.
Yes. Yeah. So you are using HG10 modes in one of the work. So can we use the higher order modes in place of HG10 modes? Is there any advantage? Even though we know that intensity is not uniform in the higher order HG modes. So can you explain that in that context?
Yes. So I mean, here I showed only 0-1 modes, but we have designed. Actually, we have a crystal even for that can have also 0-2 modes. And in general, the main advantage is that, I mean, we have the spatial degree of freedom gives us higher dimensions. But if we really want to use them, we cannot only use a 0 order or 0-1. We have to go to the higher modes. So we already have a crystal, but I don't have any results to show yet. I mean, I think it's something that we are working on as we speak. But yeah, but the main thing is, yes, we want to be able to also to manipulate the higher order modes, because this really opens all the advantages that I described of higher dimensionality, improved security, and so on.
So in the higher order modes, intensity is not uniform in all the loops.
Yes, yes.
Does it play any role there in these applications?
Yeah, so you have to take it into account in your design. By the way, also in the 0-1 on mode is already not uniform. Like here you have here you have 0, right? So this is taken into account also in the design. Like if we look at exactly here on this line, this is the axial line. In fact, ideally there shouldn't be anything. Okay, you see that there are a bit of in our design. There's nothing. The fabrication they cannot exactly do it, but it's very close to that. So yes, so we have to take it into account in what we design and also in what we fabricate.
Thank you, Arie. Thank you.
Yeah. Next questions, if there are some. Adi, while people may be thinking, let me intersperse one of my own. So when we do this crystal design, of course, these are spatial modulations it's just the refractive index of the crystal, is it? Is that all one needs to modify?
Okay.
Do we have an idea of how that's happening?
So actually, I mean, I went over it a bit fast, so maybe I can. It's good that you ask, because now I can. Just 1 second. Yeah. So what? These are the main fabrication methods. Mm-hmm. So what is done? What we modulate is the second order nonlinearity, the chi2. Mm-hmm. In fact, the crystal is uniform. If you look at it, you don't see anything. It looks like a transparent crystal. Okay. But for the nonlinear, but when you do nonlinear optics, because of the modification of the second order nonlinearity, then you get the effect. Okay. Yeah. And this does not work for every crystal. It works for ferroelectric crystals. So in ferroelectrics, you have usually, before you start, let's look at this case. Before you start, all the electric dipoles are in the same direction. And what you do is you design a mask which has the pattern that you want, and you apply electric field. This is a very high voltage pulse. Yeah. And if you do it in the right conditions, wherever you add contact of the metal with the crystal, you invert the direction of the dipole. And this also inverts the sign of the nonlinearity. And this is a permanent inversion. Then you can remove the electrodes and you have a modulated crystal. But the modulation is of chi2, the second order nonlinearity.
Yeah. So we have to modulate the chi2, right?
Yes.
Yes. And like typically, one would expect these to be like, I mean, on the absolute value of chi2, small modulations, isn't it?
So it's plus chi2 minus chi2, plus chi2 minus chi2.
Okay.
In this, yeah. You just, because once you have the dipoles in this direction, when you invert, the dipoles are in this direction. So it just flips the sign. Okay.
Yeah. And when you do the laser erasure of nonlinearity, is it the same which is happening?
Okay, so if it's erasure, it's plus 0, plus 0. So it's not as good as plus minus, but on the other hand, it's three-dimensional. So, you know.
Oh, okay. Yeah, that's clear. Further questions?
There is someone who raised his hand.
Yes, Shravan, please unmute yourself and ask your question, Shravan. You could also come on camera if you like.
Okay.
Hi, Shravan.
Yeah, okay.
Hello.
Yeah. So thank you, Arie, for the wonderful mention about like inverting the problem. You mentioned that you had adapted some machine learning tools to to come with the crystal design. I mean, are these something that is that you adapted that is already there, like the algorithms, or is it something that is already there?
Okay. Okay. For the machine learning tools. Yeah. So of course we had to adapt our problem to, but eventually what we do is we use a gradient descent, and we use standard tools. There is a toolbox that is called JAX. I don't know if you. I mean, I'm also new to machine learning, but my colleagues are using it. So it's kind of a standard tool for calculating gradients and do gradient descents. And essentially, the main idea was to find a way to formulate the problem so that we can use this standard tool. Okay, that's the main thing. So we had to parameterize the crystal and the pump, and we had to define this discrepancy measure. But once we do it, then we can just use this JAX software and get what we want.
Okay, thank you.
Yes, Adi, just RP, please go ahead.
May I ask another question? People are not asking questions, so let me ask.
Sure.
Adi, you showed this known state, and you showed two results: one by shaping the pump and one by shaping the crystal. So can you show again, like how did you shape the pump to get the known state directly from the crystal? Yeah, and. This pump.
So the idea of shaping the pump is actually fairly simple. Is we just take the laser, we split it into two, okay, and then we just have a crossed beams inside the crystal. That's it. So now this is the phase matching scheme. You see, this is the green is the pump. This is the K vector that we get from the crystal. So either we have this pair of signal and idler, or we have this pair. And the nice thing is we can use a regular crystal. You know, we don't. I mean, you mentioned correctly before that it's not easy to get the. You know, this is some kind of more unique.
Just simple splitting, and then you are mixing them. Combining them in the crystal.
Yeah. They just have to cross themselves inside the crystal.
So you have to control the pump waste here somewhere for particular pump waste only it gives, or like any beam waste it will give.
I mean, okay, we had, I don't remember exactly the number. I think we used something like 100.
No problem. No.
But I don't think it's very. I mean, the more critical issue is the angle. the pump waste, I think we selected something so that the Rayleigh range or the confocal parameter will be of the same order as the crystal. But I think it's not a very critical parameter.
It's interesting. You don't have to go far HM to get the known state.
Yeah.
Much simpler, I think. Yeah. Okay. Thank you.
Thank you.
Thanks.
Yes, there's a question from an audience, PRL Optics. Please go ahead. Please unmute yourself and ask the question.
Hello, Professor. My name is Subhit. I have a very fundamental basic question. Actually, I was wondering, so usually when we consider this light's polarization, when it comes to the classical case where we consider light as a waves, so in that case we usually take it is fundamentally the direction of oscillation of our electric field vector. But when it comes to the quantum case where we consider this single photon, how we will realize or how we will visualize the polarization of light? That is one of my question, and the one sub question also was there. So we are in quantum mechanics, while we are this heralding this photon, is like a vertical, horizontal basis, diagonal, anti-diagonal basis. In a fundamental level, which basis will be more fundamental? So that's my questions. Thank you.
Sorry, I had some problems hearing this.
Can you repeat the question? At points we lost your audio.
Okay, so my question is basically like this. So while we are considering in the classical case where we consider light as a wave, so there we consider light polarization as the direction of electric field vector. But while we are considering light in quantum optics case where we consider light as photons, so in that case how we will realize or we will visualize light's polarization, and in quantum optics where we we are heralding photons, those different cases we usually use different bases, right? Horizontal vertical basis or diagonal anti-diagonal basis or right circular left circular basis. So which one will be more fundamental if you consider a single photon?
Okay, so for polarization of single photons, I mean, it's still even if it's a single photon, this is my understanding, is that the polarization reflects the direction of oscillation of the electric field. You know, we have this wave-particle duality that holds also for photons. So as long as we don't measure them, that is, then we can still consider them as waves. So wave properties, like for example polarization, we can still use even if it's a single photon. And I guess the main difference between, let's say, a classical wave and a quantum wave, where we have a single photon, would be in measurements. For example, if you use a polarizing beam, let's say you have a photon which is at 45 degrees, and you use a polarizing beam splitter. So if it's a single photon, there will be only one click, either in one port or in the other. If you have a classical light, like you have many photons, so you have half of them here and half of them there. But in a single photon measurement, you will have only one result. I think this is the main difference. As for you know, I'm not sure I understood the other question. I mean, there are different mutually unbiased bases that we can use in polarization, as you said correctly. You can use HV or diagonal anti-diagonal, or right circular and left circular polarizations. So I don't know what does it mean, which one is more fundamental. Like they are on equal footings. It doesn't matter. You just need to choose two of them, and that's it. You are set to go. Okay. I don't know if I understood the question.
Yeah, my motivation behind that question is that so while we are considering these horizontal, vertical, or diagonal, anti-diagonal basis, usually we don't need to consider the spin orbital angular moment inherent, because it will be zero there in that case. But if you are taking right circular and left circular basis, there the spin angular momentum of photon also, it was like it was mentioning. I mean, one is +1 and another one -1. So we are basically dealing with orthogonal basis in the, while taking this left and right. So is there any specialty on that one? I was wondering this one since long time.
So maybe when you do some like some near field experiments where spin orbit coupling plays a role, maybe then there will be a difference. But if you propagate with paraxial waves in free space or using standard elements, it's the same. You know, it's just each. I can write RCP and LCP by superpositions of the, let's say, HV bases, and vice versa. So this is why I said they are on different, on equal footings. There isn't anything special that I'm familiar, at least in the paraxial case, for these three different sets of modes. But maybe, I don't know if this is what you are aiming to. Maybe when you go to very tight focus ring or some interactions in near field, maybe then you will see a difference. But I don't know. I cannot say more than that. This is what I know at the moment. Yes.
Arie, I had a question that's slightly out of the scope of our maybe talk, but it's related to you and other work you do with electron beams as well. So when it comes to imaging, especially, you had mentioned in one context that the noon state is well adapted to doing super resolution imaging. So are these some of these ideas portable to the electron imaging domain as well?
So it's an interesting question. I'm not familiar. I mean, first of all, there is some fundamental issue that electrons are fermions. So I don't know. I don't think you can have n electrons in the same mode, n identical electrons in the same mode. But if we go to, let's say, all these concepts of quantum illumination or quantum imaging, so there are some works on trying to implement, these ideas also with electron beams. And the main motivation is that, let's say, you want to look at, I mean, in general, electron beams in microscopy, you can have much higher resolution. With electrons, you can get to atomic resolutions. So it's like four or five orders of magnitude better than optics. But the problem is what happens if you want to look at the biological samples. Mm-hmm. So then usually the electron just kills your sample, the electron beam. So then there is some motivation to do imaging or microscopy with very low illumination, or even in principle there are these ideas of interaction-free measurements that you will map your object without ever interacting with the electron will never interact with the. Okay. So this is all these ideas are under the, let's say, the title of quantum electron microscopes. Mm-hmm. There are some groups that work on it. For example, Mark Kasevich in Stanford is working on these ideas.
Okay. Yeah. Further questions? Okay, I guess we also had a fairly extensive discussion. So
Thank you. Yes.
yeah, indeed. Thank you so much, Arie, for really opening many new vistas today with your talk. And as I said, it's the festival of colors here. So we indeed have did full justice to it by using nonlinear optics and in the quantum domain. So I guess that really brings this session to a conclusion, but possibly also more of a beginning for many young students here, especially in India, who join your seminar.